All right, so wireless communication has been developing for over 50 years. But have you ever tried to place a call during a storm and it didn't go through? Maybe even yesterday? Well, it turns out you're not the only one, and it might just be because of 5G. And that's what we discussed this summer and tried to figure out. Now, as for who we are, I'm Archisa, this is Prakshab, that's Despoina, that's Mark, and that's John. Now, going back to what I was saying about 5G. 5G uses millimeter waves in the FR2 range, which is 24.25 gigahertz to 52.6 gigahertz, among others. Now, what happens is that at such high frequencies, these signals tend to behave in uncharacteristic ways, notably when water or rain is obstructing them. That's why this summer we decided to figure out why your phone might not have worked yesterday by analyzing channels and their behaviors at certain these frequencies, but also by figuring out how obstructions from rain affect the signals being transmitted with these two experiments.
So one of the key hardware we used for this project was a thing called the PAMS, which stands for Phased Array Antenna Module. You can see over there next to the water jug, that's one of the PAMs we used in the first couple of weeks. Then in our outside experiment, as Prakshap will be showing, is the one we use outside. So this transmits various types of signals, but the key part about it is it allows us to do a technique called beamforming, which allows us to transmit a signal in any direction we want to. Also, this PAM allows us to transmit in 28 gigahertz, which was the key part about this experiment. So another key piece of hardware that we used was the spectrum analyzer. Sadly, it's not here today, but this piece of technology helps us visualize those signals. And also paired with an antenna, it helps us detect the signal frequency and test the signal quality of the signal.
Yeah, so primary software they use throughout these experiments is GNU Radio. As people have mentioned before, GNU Radio is an open source software development toolkit specifically for interfacing with software-defined radios. So this is on the user computer and configure USB devices that we use to either transmit or receive signals using the PAMs. Yeah.
So one of the ways that we got useful data out of both the spectrum analyzer and GNU Radio is using programming languages like Ruby and MATLAB. Ruby was the programming language of the spectrum analyzer, and using code with that, we were able to take a bunch of samples in our measurements, and then using MATLAB, we were then able to visualize those. That graph is an example of that, and it looks much better than just a giant Excel sheet of numbers. Another part that we used was Python. As Proc mentioned before, the GNU Radio was the whole brains running this experiment, but the data it outputs is in a binary format, not very readable, not usable. Python allowed us to extract that data, convert it into a meaningful numbers that we were then able to visualize with other things, and also feed into our machine learning model.
So this leads us to our first experiment, which is to measure the power loss over distance within our mobile PAM. So our primary purpose of this is to capture data on our spectrum analyzer, automate data collection with Ruby, as Mark mentioned, and also process and visualize this data with MATLAB later. So as you can see on the setup that we did on the grassy field outside of WINLAB, we have the receiver end here with the spectrum analyzer and the antenna, and the transmitter end over there with the mobile PAM, as you can see. And all of this is hooked up to Wi-Fi so that we can remotely access into this using Chrome Remote Desktop. So experiment one essentially entailed transmitting sinusoids using a GNU radio on the PAM device, and then using a Ruby script, as Mark mentioned, to sample screenshots of the spectrum analyzer to then post-process later. Between each transmission, we move the PAM device a certain amount of distance backwards, whether it be 2 meters, 5 meters, or 7.5 meters. And then we have the data stored locally to our computers.
Like Proc mentioned, we used the Ruby script to extract all the data from the spectrum analyzer to an Excel sheet. Then using MATLAB, we were able to find the peaks between the transmitter and the receiver, but also find the power loss in those transmissions. But the also problems we faced during this project was that the Wi-Fi kept on disconnecting. This wasted a lot of time, and the spectrum analyzer consumed a lot of batteries, so we had to cut the project short. Another problem that we faced was that the mobile PAMs was not calibrated correctly, which caused an IQ imbalance and distorted our results. So future plans for this project is to execute this project in various distances and as well as different frequencies, such as 29 gigahertz and more, but to also incorporate the water jug in this project.
Now, after a day out in the sun, we finally came back inside and did some other experimentation to detect water interference in sandbox 1, as you can see here, and the PAM in the back corner. We transmitted between PAM 2 and PAM 1, and we had a variable of a full water jug versus no water jug at all. After that, we processed signals, collected sync-word and pilot data, created a data set, and then also did classification. So here is just the setup of our experiment. It was with a full water jug or no water jug, and we like to call it the Juggernaut project because it's like jug or not. But this is the setup for it, and we did account for just the plastic causing an interference in the signals by having just an empty jug as for measurements as well during the experimentation.
So the big picture here is that in wireless communications that use OFDM, which stands for orthogonal frequency division multiplexing, it is common practice to use sync words for synchronization and pilot carriers for to facilitate channel estimation and correction. And these are the exact features we wanted to make use of in order to properly detect water presence in the channel. Because we expected the water to cause changes to them. So what we want to emphasize here on the receiver flow graph we used for GNU Radio is this block over here, the demultiplexer, which splits the frames into header frames, which contain the sync words, and payload frames, from which we extracted the pilot data. And so to create our data set, we extracted the information I talked about, and then we grouped it to form the samples. And we only used phase information because we hoped that this way the models would generalize better.
So as I previously mentioned before with the Python script, automating this part of the data collection was a huge part of our efforts and definitely streamlined the whole process as we continued. As I said before, it takes the binary data, and this one actually was using a text message. So I converted the binary data into the raw received text format, cross-correlated that with a known text message, and then we did that for the purpose of using some sort of statistical or probability-based method to determine if the message was accurately transmitted and received.
So finally, as far as the classification is concerned, we first applied principal components analysis on our data set and reduced the dimensions to around 15 components for more than 100. And then we trained several simple classifier models. And with the best of them, we achieved an F1 score of around 80%, which we believe means that the result is encouraging and that it does indeed stand as a proof of concept. Of course, more testing is needed. The dataset needs to be enriched to further make the model better. And it would be interesting to try to reason through the classification process.
Now, no project is complete without a future to the project. And for our future, we would like to have some diversification of experiment, which includes more outdoor experiments. And what we want to do is measure at different distances, different frequencies, and more variables of like water jugs in between as well. We also want to collect practical data to refine the model because that's just a jug, but we want to go into the Rutgers Rain Lab and simulate the actual experience of rain. And yeah, thank you so much. And we look forward to answering any questions. Thank you.
For this model that we have tried here, it was 136. Yes. I think, yeah, there was an initial PCA analysis that captured 95, but after that, we kept even less than them. So yeah, the data set was not very varied. So we wanted to keep as least components as we could to actually make sure it generalized. So yeah, we are pretty confident that it can get much better than that.
from the analyzer data went into the Excel, right? And then you ran it into MATLAB and visualize. Why wouldn't we use, like, for example, Panda and Matplotlib? What do you need, like, special toolbox for that?
Yeah, that.
While we had first done this with MATLAB, I didn't really realize that this could be done with Python, and my Python skills weren't really that strong at that point. So I just went with what I knew. But then after that, yeah, some of the cross correlation we were able to then plot and visualize using Python alone.
I'm wondering why you got for R. Yeah. Thank you.
Thank you.